This last interference situation we're talking about is called a diffraction grating. So it's similar to a double slit where we had two vertical slits side by side. What it is, though, is a whole heck of a lot of slits side by side. Typically, our diffraction gratings are listed as some number of lines per centimeter or millimeter, which is essentially saying number of lines in some length. So if we were to come to our diffraction grating and measure the length of a certain segment, there would be some specific number of lines in here. So for example, let's say we had 650 lines per centimeter, if that's what the grating was rated at or labeled. The distance, so coming back up to the picture, what we care about is the distance between one slit and its neighboring slit. The distance between slits also the lines. D would be 1/650 centimeters. It's the inverse of whatever that grating is labeled at. If we wanted to convert this, we know there's 100 centimeters in a meter. So this would be, if we solved for D, I'm going to change my mode to scientific so I don't have to count decimal places. Would be 1.538 times 10 to the -5th meters. So these lines are incredibly close together. If you recall, so total side note, our double slit pattern, we could determine the location of the bright spots or bright lines in the pattern using the equation m lambda L over D. M was our multiplier, m equals 0 was our central maximum. So if we're talking about the bright spots or fringes, m was our multiplier. M equals 0 was our central max. M equals 1 was the distance to the first bright spot on either side of that central max. D down here was the distance between the slits. If D was small, Y was big. So essentially, with this diffraction grating, not only do we have more slits, but these slits are really, really close together. Diffraction gratings show us very specific points of constructive interference that are widely spaced. Found a little video clip to show you. This one, the person has a green laser light. Right now it's just shining on some sort of screen. It's also reflecting on the table. So the bottom oval part, don't worry about that. That's a reflection. We want to specifically watch what happens to the dot in the back.
We are on top of a laser right now, and this is a diffraction grating, and when it is introduced into the laser beam, it produces a diffraction pattern.
Okay, so pausing, the very brightest spot we see above that white border is the central maximum. That's where we would define y equals 0. And then there's two bright spots on either side, to the right and to the left. Those would be the first maxima. And then he started to move the slide, but we saw the additional bright on the right or left. As he moves the slide, that changes L. L remembers the distance between the slits and the screen, where we're seeing the pattern. So if you change L, that changes Y also. So he's decreasing L, which is decreasing the distance to those bright spots. Now he's increasing it, which increases the Y value. Because he's using a laser, it is one specific wavelength, which is why we see very specific points of constructive interference. If we have white light, and then fast forward, this is our same demo friend that I showed for single and double slits. I'm not going to show this whole video clip, it's kind of long, but it's actually really cool to watch. So I'll link the demo to the demo in the list of videos. So if you are interested, you can watch more. But I want to show you just the beginning part.
To show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. So it's called a grating, just like a street grate, it has lines through it, and this allows you to resolve the spectrum of a source of light in the same way that prism will resolve a spectrum. So what we're going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with a diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left, you'll see a rainbow spectrum that shows what wavelengths are present.
So when he mentions a continuous spectrum, this incandescent light bulb emits all of the wavelengths of light, all the different colors, all the wavelengths, which is why we see a complete rainbow. Okay. He also is going to show some different gas tubes which emit very specific wavelengths. I'll play this long enough to see one of them. You can watch more.
In this, you'll see, as you look on the right side, violet through all the colors of the spectrum, all the way through red. So that's a continuous spectrum. We'll try next to look at a discrete spectrum of mercury. Now, what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. So I'm going to locate this proper spot, turn off the continuous spectrum. So this is a mercury spectrum without the diffraction grating. Let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum.
So the mercury gas here is emitting specific wavelengths of light. The blue, the green. He goes through and shows nitrogen, I believe, neon, hydrogen. So again, I will link to this video so you can watch that later. Diffraction gratings are extremely helpful in spreading light out into its various components. The continuous spectrum meant that all wavelengths were present in the light. That was from the incandescent light bulb, was the terminology from that bulb. It would be the same as far as our eyes to look at the sunlight. If you do have the equipment that is sensitive enough, sunlight actually is considered a discrete spectrum as well. Discrete spectrum meant specific wavelengths are present. And that is fundamentally due to how the particular element, its electron structure and electron energy levels are presented. So that's more of a modern physics, a quantum physics type discussion that we're not talking about. Ultimately, what we want to know at this point is that a diffraction grating is going to give us a pattern that has a bright central max. If we're talking about shining light of one specific wavelength, on either side of the max, there will be a first max. We call it a first order max. And then potentially there's a second order on either side, which I would be off my screen on the right side. So in terms of equations, we're still going to say y equals 0 is the center of the central maximum. If we measure from the central maximum over to the first order max, and this is true on either side, we would call this y1. If we were to measure from the central max over to the second order max, this would be a y2. So the definition of y is the same. We're going to have a d to represent the distance between one slit and its neighbor, which is going to be really small in a diffraction grating. L is still going to be the distance from the slit to the screen. The biggest difference here is that our angles, when we talk about a theta sub m, is not small. In our equations, to come up for the single slit and double slit pattern, for example, we had theta sub m was m lambda over d for the bright fringes. And we could say this, where theta was in radians, because the angle we were talking about was so incredibly small. That small angle approximation tells us that the sine of theta and the tangent of theta and theta itself, when measured in radians, are the same thing. But when we have a diffraction grating, that is no longer the case. So when we get to the point and say that delta r, the difference in distance that one wave travels compared to another, it is d sine theta. It has to equal m lambda for constructive interference. All that means is we have to leave the equation this way. Or we can say sine of theta is m lambda over d. We cannot erase the sine. We have to leave it as sine of theta. Similarly, we showed in the first video when we were talking single slits that the tangent of theta was equal to y over L. What this means is we're going to have two equations. We have our sine of theta sub m is m lambda over d, and y sub m, the location on the screen, like we were talking about in this picture here, will be L tangent of theta sub m. M can be 0, which just gives us a central maximum. If M is 0, we end up with y is 0. So that means the central maximum. If M is 1, that gives us the location of the first order max, the first maximum on either side of the central one. M equals 2 would be the second order, the second maximum to the side from the center, and so forth. These equations are specific to a diffraction grating. Lambda is still the wavelength of the light that we are shining through the diffraction grating. D is the distance between the slits. L is the distance from the slit to the screen. Y is the distance on the screen measured from that central max to the bright spot that you're talking about. Different wavelengths will have different diffractions, so different y values. And that's why in the video clip that showed the incandescent light bulb with the continuous spectrum, we saw a rainbow. All the different wavelengths within the rainbow had different y values on the screen. And so similar to a prism, the diffraction grating spread that white light out into the prism. Diffraction gratings, this concept is also very common in nature. If you've ever seen a peacock, the beautiful birds with their beautiful feathers, the different colors we see are due to, it's more of a reflection grating, but it's the same idea. If you've ever looked at the back of a DVD or CD or compact disc, or that was a CD, sorry, Blu-ray, if anyone even uses those anymore since we stream everything. If you look at the surface and hold it just right, you can see a rainbow reflecting back to your eyes. That reflection grating is very similar to what we're talking about with the diffraction grating. It's just dealing with light reflecting. The different wavelengths will reflect at slightly different angles. So a lot of different things, beetles, a number of beetles and the different colors they have. The peacock with the different colors in its wings. That's true for many butterflies and birds. The beautiful colors we see are because of how the different wavelengths reflect back towards us. So it's the structure of the actual wing or surface that we're looking at. Okay, so we have single slit interference, circular aperture, double slit, diffraction grating. I'm going to go through examples as well. I decided I'll do all the examples at the end because all the concepts are extremely similar. So really it's going to be a matter of making sure we know how to choose the right equations for the different examples.